Hi y'all, it's the last video, so I hope you've enjoyed this class. And again, as always, please reach out if you have any questions, especially before the final. So we're going to finish off chapter 19 and then we're done. All right, so just some things to remember for spontaneous reactions to proceed in the forward direction, which is towards the products. Remember, delta G should be negative, E should be positive, and K should be more than 1. All right. Also, hopefully you remember the negative RT, L, and K when we did delta G last chapter in chapter 18. Now we've got a new one where we've got NFE, negative NFE. Okay, and N is the moles of electrons, and it needs to be total moles of electrons. So if you do multiply a reaction, make sure you're paying attention to moles of electrons. Also, this Faraday's constant is normally, we normally just use 96,500. That's what I type into the calculator. And this little triangle just shows you how to get from one thing to another. Okay, so is it spontaneous? Calculate delta G, but all they did was give us a reaction. So the first thing we need to do is find E cell, and it's going to show us our chart. All right, so we've got I2, gotta find it. I2 is, so I2 plus 2 electrons is 2I minus, and that is 0.52 volts. And then 2Br minus yields Br2 plus 2 electrons. Move this over some. Okay, for bromine, we're looking at, because I flipped it, it's going to be negative 1.09 volts. Okay, so this one I can already tell you is not spontaneous, just based on the E cell. I get negative 0.57 volts, but it didn't only want that, it also wanted delta G. So delta G is equal to negative 2, that's N, times 96,500 times negative 0.57. And I get 110,010. And this comes out in joules, y'all, and that's because volts is in joules. It's a derived unit, so it's got some joules in there. So remember, delta G is normally in kilojoules, so just pay attention to that. So you can either leave it at 110,000 joules or 110 kilojoules. It's not letting me write there very easily. There we go. I think it's just because it's at the bottom of this slide. Okay. Yeah, I read a number off, but it's still very close. Not spontaneous. Okay, here we have sodium and water. We want to know if it's spontaneous. So sodium is going to Na+. So I do not see sodium on my chart. So, in the event it's not on the chart from the book, I promise it'll be on the chart from the one that I posted in week 4, because it has everything you could possibly need. All right, so if it's not on this one, look on that one. Okay, we want to know E cell, but we also want to know K. So here's our chart. I need copper and hydrogen. So copper Make sure you find the right equation. This is 0.34 volts. And I need to flip it, so that one's negative. I've got 2H plus 2 electrons yields H2. And that just happens to be 0, so I'm going to add these, negative 0.34 volts. Okay, so this one's not spontaneous. If it were me, I would go through G, but they do give you this equation. So we can go ahead and, so 0.0592 times our voltage divided by N, which is 2. Nope, sorry. This 0.05292 volts, that's it. So our E cell, so I've got negative 0.34 is equal to 0.0592 over 2 electrons times log K. Okay. Okay, I get that log K is equal to negative 11.48. Remember, the opposite of log is 10 to the. So I get that K is 3. Let's go with 3.3 times 10 to the negative 12. So this is also considered not spontaneous, and that's because we've got that less than 1 K value. It's going to proceed in the reverse direction. All right. So again, if you need more practice, please let me know. I've got tons. And there is a situation when your concentration is not 1, and then we're going to use this different reaction. It's called the Nernst equation. Okay, and just remember that the degree sign means we are in standard notation, but then we are not when we do not have that, and so you've got to use this. Remember, Q is products over reactants from chapter 15. Okay, don't forget to raise them to their powers. This is the equation we're going to use. Okay, and remember our temperature is in Kelvin, but it gave you all those values plugged in already. Okay, so here we're calculating it under non-standard conditions, and here are our values that are our not standard conditions. They're not 1. Do notice, though, that 4 is 1, or the H plus is 1. Trying to get the E cell. This one did not give us E cell. Okay, so here's our E cell, 1.34. So I'm going to go back. It told us, so E cell is 1.34 minus 0.0592 over, this one has 6 electrons total. And the reason it's 6 is because there's 3 and 2. Okay, so make sure you multiply properly, because that's going to be taken into account. I just want to see the direction. So our copper is a product. Okay, so our copper is the product, and there are 3 of them, so it's 0.01 cubed. And then our manganese, or our permanganate, is 2 squared times 1 to the 8th, but that's just 1. Okay, and I get that E cell at the end is 1.49 volts. Okay. Theirs is 1.41. It's possible that it was my calculator because I'm using a scientific instead of my normal graphing. So just double check. It's always easier when you use a graphing. Okay. But this is called the Nernst equation. The ones, I think there's one on the test, and it's not a big one like this. It's like one on each side. There's a reactant that has one and a product that has one. That's it. All right, so just an overview of electrochemical cells. Remember, oxidation occurs at the anode, reduction occurs at the cathode. In voltaic cells, remember it's spontaneous, E cells positive. The anode will have that negative charge, and the cathode will have that positive charge. In electrolytic cells, which is not spontaneous, that E cell is going to be negative. Okay, and please notice in both these cells, the electrons always flow from anode to cathode, but in one of them it has a battery as a source, and the other one it's the voltmeter, which is just reading the voltage. In electrolysis, that's the process of using electrical energy to break apart a compound. This is how we get water broken into hydrogen and oxygen, and that is only done in electrolytic cells because they have to have energy to make that happen. Notice the battery in the picture. I'm not going to ask any electrolysis questions, but electrolysis is normally the opposite of the spontaneous process. And the reason we would do this, we can produce hydrogen for fuel cells. This is how we plate different metals. I'm sure, ladies, if you're wearing any silver jewelry, it may not be silver, it may be white gold, which is a plating process. And then metal extraction from minerals and purification. And some electrolysis reactions will require more voltage than they predict, and that's just called overvoltage. The source of energy is either going to be a battery or DC power. And for electrolysis, the terminals are flipped. So the positive terminal is then with the anode, and the negative terminal is with the cathode. Here's just it walking you through some, but again, you're not going to have to do any calculations. And sometimes they do this with salts as well, but they're molten salts, so they're in a liquid state instead of in that dissolved state. Okay, it wants you to predict the half reactions, but you're not going to have to do this, so we're just going to keep going. And then electroplating, this is when cations are reduced at the cathode, and they plate to the new surface. And the anode is made of that plating metal, and the anode will oxidize the metal cations. So when we have mixtures of ions and electrolysis, the cathode is the least negative or most positive, and the anode is the least negative or most positive. Hang on, something's wrong. Oh, because they're flipped. It's weird to read them that way. But remember, the table you have is a reduction table. So for the cathode, it's the least negative or the most positive. And I'm going to put least positive. Well, let's do most negative or least positive. Okay. This is the last topic. This will be on your test. It'll be on the homework, is the stoichiometry that goes with electrolysis, which is important for y'all to know. So just keep in mind an amp is a coulomb per second. And that Faraday's constant, remember that's 96,500 coulombs per mole of electrons. Okay, so they're going to give you a time, they're going to give you a current, and we're going to need to find mass. Just remember that amps are coulombs per second, and the amps has 2 units. You always want to start with the unit that has 1. So 25 minutes is our first starting point. you've got to get minutes to seconds because amps is in seconds. And then we could use our amps. So our 5.5 coulombs per 1 second. Once we get to coulombs, you need to use Faraday's constant, but it's got to be on bottom. It's 96,500 coulombs per 1 mole of electrons. As we're looking in this reaction, notice there are 3 moles of electrons. So there are 3 moles of electrons in 1 gold. And then it wants grams. So 1 mole of gold. And of course, I took my periodic table out of here. I've got textbooks though. So gold's mass is 197. It's just not one that we use often. Grams. Okay, so just remember from stoichiometry, multiply across the top, divide by the bottom. I get 5.6 grams of gold, which is actually a whole lot of gold. Now, we did run it for 25 minutes, but still that's a good amount of plating. 5.6. Okay, you can also go the other direction, which is what this one did. Notice they gave us grams. So we've got 12 grams, and that's of Ag, so silver. There's 1 mole of silver. I'm going to have to get back up and get the periodic table. So in 1 mole of silver, there's 1 mole of electrons. And then we use 1 mole of electrons is coulombs, Faraday's constant. And then remember, an amp is a coulomb per second. So I've got 3 coulombs on the bottom in 1 second. And notice this one asked about minutes. So I need to get 60 seconds to 1 minute. I think gold is 107. Sorry, silver. It was 107.9, so we're looking at 108 for the math. All right, so again, we do our math. I get 59.6 minutes. So this is about double the amount of time, and it's about double the amount of product. So, okay, it's a good, easy way to check. Then corrosion. Just remember that corrosion is going to be a spontaneous oxidation. Remember from equilibrium that it goes both ways, but only one direction is going to be spontaneous, and it's going to be the resting direction. Okay. This is just an explanation. So that's it. Y'all have a great rest of your semester.